Have you ever wondered how we can plant crops more efficiently? Hi, I'm Junro,
And I'm Mingzhou.
and we are from Sunway International School. We will be presenting about our experiment on developing salt-tolerant rice for a sustainable future. There will be 4 sections in this presentation, including introduction, experiment, analysis, and last but not least, the conclusion.
So, firstly, the introduction. So, what is the problem faced by Malaysia or even globally upon crops? Kedah is known as the rice bowl of Malaysia, producing about 43% of the country's homegrown rice. Many farmers in Kedah rely on rice farming to support their families and livelihoods. In addition, the Kedah state government plans to increase rice production to prepare for potential global food security crises. However, these plants are threatened by climate change and human activities like excessive groundwater pumping that exacerbates saltwater intrusion.
The sea level rise leads to seawater breaches, increasing the salinity in paddy fields. As a result, up to 75% yield losses since 2016 in coastal areas like Kuala Kedah. For farmers who solely depend on this production, this means economic hardship and uncertain futures, jeopardizing food security and livelihoods in Kedah.
Before we dive deeper into possible solutions of this issue, let us learn about the effect of salinity on seeds. For seeds to successfully germinate, it requires the absorption of water through the seed wall via diffusion and capillary action. Water will move from outside the seed wall to inside the seed wall through osmosis.
The salt itself may also affect germination through ionic stress, which disrupts enzyme function, metabolism, hormonal signaling, and energy reserve utilization. In conclusion, the overall effect of salt stress on seed is to delay and inhibit germination.
Halo priming is a possible solution towards the issue of increasing salinity in water bodies. For those who don't know what halo priming is, it's a method that involves soaking seeds in specific salts to enhance germination under saline conditions. It improves seed germination and seedling emergence in salty environments by triggering physiological responses that enhance plant stress memory, therefore enabling plants to respond more effectively to future environmental stresses.
In this investigation, calcium chloride was chosen as a priming agent. Calcium is known to inhibit sodium uptake, reducing the adverse effects of salinity on seed germination. This makes calcium chloride a promising agent for enhancing salt tolerance in rice crops.
The saline environment for testing Oryza sativa seeds, or rice seeds, was a controlled sodium chloride solution. It was chosen as it is a dominant salt in saline agricultural soils, particularly in coastal areas affected by sea level rise like Kedah. A fixed NaCl concentration will mimic real-world saline soil conditions, providing a consistent osmotic and ionic stress on the seeds.
So, how does this issue align with the Sustainable Development Goals? Firstly, SDG number 2, Zero Hunger. As this issue is being addressed and solved, it can help combat hunger through increasing agricultural productivity and ensuring food security in saline-affected areas.
Number 12, responsible production. This promotes sustainable agricultural practices by enabling the use of lands affected by salinity.
Number 13, climate action. By solving this issue, it can increase resilience to climate change impacts such as rising sea levels and soil salinization in coastal and arid regions.
Last but not least, number 15, life on land. This would help protect and restore terrestrial ecosystems by preventing land degradation and desertification in saline affected areas.
These are all the materials needed for the experiment. And this is the methodology of the experiment. Firstly, soak the rice seeds in 1% of sodium hypochlorite, rinse, and then dry it. Then, use 6 different concentrations of calcium chloride to soak the seeds for 12 hours. Allow the seeds to germinate in a petri dish, and data should be recorded afterwards.
There are a few ethical considerations to be addressed in this experiment. Firstly, all the seeds in this experiment were handled with care. They were transferred carefully using dowel tweezers, and all germinated rice seeds were transferred to soil for further growth after the experiment. In addition, no seeds were disposed of, and the exact amount of seeds needed were purchased to prevent waste. All chemicals used in this experiment were also diluted and disposed of properly to prevent pollution.
The result of the experiment shows that the higher the concentration of calcium chloride used in the halopriming process, the higher the average shoot length of the seedlings. However, for calcium chloride concentration of above 2.5%, seed germination was disrupted, causing a fall in its shoot length. This could be due to excessive stress at higher concentrations, which inhibited growth.
For higher validity and reliability, a statistical test, the one-way ANOVA, was performed. The results had shown that there is a significant difference between experimental groups, and the null hypothesis can be rejected as seen by the p-value being less than 0.05. In conclusion, it was proven that halopriming improves rice seed germination and growth as measured by its shoot length, as long as the concentration of calcium chloride is kept below 2.5%. Therefore, farmers should consider pre-soaking their seeds in ideally 2% diluted calcium chloride to enhance paddy yield in areas affected by saltwater intrusion. This strategy can do a number of things, such as increase crop resilience, improve productivity, and secure the livelihoods for farmers facing the challenges of salinization. However, in regions not affected by salinity, halopriming may introduce undue stress on the seeds without any significant benefit, so it is crucial to assess local soil conditions before application.
That's all for our presentation. Thank you for listening.